Hello everyone, my name is Seow Ling. Today I would like to share on INE 504 project and presentation. The topic is the type of surface emitting laser. As we all know, laser can be edge emitting laser or surface emitting laser. The type that I'm going to focus today is surface emitting lasers. Here are the three journals that I've chosen. The first one is Narrow Line Width Surface Emitting Distributed Feedback Semiconductor Lasers with Low Threshold Current. And the second one is Investigation of Single Mode Vertical Cavity Surface Emitting Lasers with Graphene Bubble Dielectric DBR. And the third one is effect of gallium phosphide barrier on efficiency enhancement of 860 nanometer vertical cavity surface emitting laser. And below here are the references. Let me begin with first journal discussion. The first journal title is Narrow Line Width Surface Emitting Distributed Feedback Semiconductor Laser with Low Threshold Current. Here is the executive summary. Surface emitting distributed feedback, abbreviated as SEDFB laser, is widely used because of its advantages like high power, high beam quality, and narrow line width. However, this laser had its limitation in terms of output power, stop efficiency, threshold current, and divergence angle, mainly because of its unoptimized structure. Thus, in this research, the SEDFB laser is simulated and fabricated with an asymmetric waveguide layer accompanied with second-order grating. In order to obtain SEDFB laser of wavelength of 980 nanometer, simulation result shows that the optimized second-order grating structure is 300 nanometer of grating period, 0.4 of the duty cycles, 380 nanometer of grating depth. The fabricated SEDFB laser obtained with wavelength of 980.1 nanometer, while the threshold current, output power, and slope efficiency are 300 mA, 1.22 watt, and 0.45 watt per ampere respectively. The fabricated laser performance is slightly lower compared to the simulated result, which could be due to the thermal energy generated inside the laser or the defect in thickness or doping concentrations. Here is the research methodology or the process flow. It begins with the simulation by using software. It can be divided into two parts, which are second order grating simulation, which is to determine the grating depth, the periods, grating periods, ridge width of grating. Next is the SEDFB laser structure simulations. This is to simulate the performance of the laser in terms of output power, stop efficiency, and the threshold current with the duty cycle of the grating. Next, we proceed to the grating fabrications. Grating referring to these parts. It is fabricated by using electron beam lithography technique. It was then transferred by inductively coupled plasma ICP etching technique. Next, followed by the characterizations. Using SAM, this is to check the surface pattern and the cross-sections pattern as well as the dimension conformations. After finish with grating fabrications, next we're going to focus on P electrodes. Overall, this epitaxial structure is grown by metal organic chemical vapor deposition MOCVD. And the top part is etched until it left with this ridge width of 100 micron and depth of 300 nanometer via ICP etching. And then it followed by the silicon dioxide depositions. A 250 nanometer thick of silicon dioxide insulation is deposited around the ridge. As for the current injection window is then formed in the second order grating region on the ridge. Lastly, P electrode depositions. P electrode layer consists of titanium, platinum, and gold layer, and the thickness are 30, 30, 150 nanometer respectively. Okay, after done with P electrode, next is N electrode. referring to here. So the substrate is thinned down to about 130 micron in order to achieve the emission from the surface of substrate. And then a window of 100 micron times 600 micron window is fabricated at the center of the substrate by the up-down alignment ultraviolet exposure technology and metal lead-off technology. As for the N electrode depositions, nickel, gold, germanium, nickel, gold metal contact layer is deposited. The thickness are 500, 45, 300 nanometer respectively. After finish with N electrode deposition, the next part is laser packaging. The epitaxial structure is cleaved into 500 micron times 1000 micron chips, and the chip is then bonded to the copper heat sink through the indium solder to dissipate heat, and the gold wire is drawn from the chip surface to form electrodes. Next is characterizations. A few characterizations are performed, which include light current voltage measurement, conversion efficiency measurement, wavelength and intensity measurement, far field divergence angle measurement. Next, we proceed to result and discussions. Figure 1 shows the stem images of the second order grating. So we can see from figure 1A is the top surface of the grating, and figure 1B is the cross-sectional of the grating. The grating period, duty cycle, and the grating depth are measured as 301.3 nanometer, 0.41, and 382.2 nanometer respectively. Based on the calculation and analysis of equations, equation used is over here. The grating period, duty cycle, and grating depth are 300 nanometer, 0.4, and 380 nanometer respectively. The difference between the calculated and the actual dimension is small and acceptable, as it has a little effect on the device performance. Usually, the fewer periods of second order grating, the lower the lasing threshold because of the small out coupling loss. Next, we proceed to laser characteristics of SEDFB laser. Figure 2A shows the light current voltage curve, while figure 2B shows the conversion efficiency. From the figure 2A, black color line here shows the relationship between output power and current, while the blue color line here is the relationship between voltage and current. From the black color line here, we can identify the threshold current. The threshold current is around 0.3 ampere or 300 milliampere. The continuous wave output laser power from substrate achieve 1220 milliwatts with the current of 3 ampere and the voltage of 1.73 volts. The slope efficiency is around 0.45 watt per ampere. Figure 2B shows the maximum conversion efficiency of 26.6%, while the average is around 25%. Next, we proceed to discuss on plots of wavelength against spectral intensity of SEDFB laser. So, figure 3A shows the 1 ampere current result, and figure 3B shows the 3 ampere current result. So when the current is at 1 ampere, the lasing mode is multi-mode, and the spectral intensity becomes stronger at around 980 nanometer. When the current at 3 ampere, the center wavelength is at 980.1, and the line width or the full width at half maximum is at 0.84 nanometer, and the side mode suppression ratio is close to 29 dB. So this last part I'm going to discuss on far field divergence angle spectrum of SEDFB laser. So from the spectrum here we can see that blue color line is the Y direction, red color line is the Z direction. Full width at half maximum for Y directions is 5.5. Z direction is 1.8. So far we can see the directions is consistent. So we can conclude that the far field divergence angle is 1.8 degree times 5.5 degree, which is much smaller than the edge emitting semiconductor laser, which has been reported as around 30 to 60 degree times 10 to 15 degree. So we have finished for the first journal discussion. This is the second journal topic, investigation of single mode vertical cavity surface emitting laser with graphene bubble dielectric DBR. Let me begin with executive summary for this second journal. Vertical cavity surface emitting laser VCSEL are famous in the development of the functional integrated optic because of its high efficiency coupling with fiber. VCSELs usually exist in multiple transverse mode. Single mode VCSEL face challenges to be fabricated because it requires a smaller cavity cross-section, consequently a decrease of active volume and output power. So in this research, VCSEL was fabricated with an 850 nanometer intercavity contact single mode and a graphene-assisted self-assembly curved dielectric bubble back mirror. The low cost of dielectric bubble DBR, which is made up of silicon nitride and silicon dioxide, was deposited on top of the graphene half VCSEL structure via van der Waals force, without any additional spacing element or sacrificial layer release edge process. Because of graphene uniqueness, graphene is having low surface energy. The single mode output power and slope efficiency of continuous wave operating VCSEL with an aperture diameter of 7 micron are more than 1 milliwatt and 0.2 watt per ampere respectively. These novel graphene modifications into laser can also be applied to other optoelectronic devices such as resonance photodetector and super narrow line width VCSEL. Next, I'm going to share on the research methodology for this second journal. It can be summarized into 4 main steps, which are half VCSEL fabrications, graphene layer depositions, silicon nitride and silicon dioxide layer depositions, and then complete. For the first part, half VCSEL fabrications. So we can see from the figure here, half VCSEL consists of the bottom part here, which have bottom mirror DBR, quantum belt, which is the active regions, optical confinement layer, which is the oxide layer, and P mirror DBR. So this part is fabricated by using standard laser fabrication process MOCVD. Next is the graphene layer fabrications. The graphene films were grown on copper for using CVD. A thin layer of PMMA was coated on the top of graphene film, followed by the etching copper foil by copper etchant. The graphene PMMA film was transferred to half VCSEL substrate. Optolithography applied to pattern the graphene electrode layer by oxygen plasma. So after complete the fabrication for graphene, next we proceed to silicon nitride, silicon dioxide layer deposition. So 7 pairs of this mixture layer were deposited by plasma enhanced chemical vapor deposition PECVD. The bubble DBR was formed due to the built-in strain increasing. After finish this part, the whole thing is subjected to characterizations. Characterization performed are SAM, Raman spectroscopy, light current voltage measurement, modulation frequency measurement. Next, I'm going to share on result and discussion for this second journal. Figure 1a here, we can see that this is the SAM images of half VCSEL structure after graphene was transferred onto it. This confirms that the transfer process of epitaxial graphene layer is complete. Next, figure 1b, this is the Raman spectrum of graphene. Based on the peak over here, we can see the 2D peak having higher intensity compared to the G peak. This suggests that the presence of monolayer in graphene. Also, there is no D peak here, which indicates there is no defect or damage during the transfer. Let us continue with physical characterization discussion. From figure 1c here, this is the images taken by optical microscope as well as the curvature surface scan of graphene layer. From this scan, we can see that the graphene layer is observed with an approximately 4.5 meter curve upwards. As for the figure 1d, this is the same images. We can see there is a bubble DBR here. This is because the silicon nitride silicon dioxide DBR on the graphene surface induces an accumulated internal built-in strain, resulting a weak adhesion onto graphene. Therefore, silicon nitride silicon dioxide DBR find an air gap on the graphene surface, and the DBR is inherently formed at the center of the oxide aperture. This air gap is very important to improve the carrier mobility via ballistic transport of graphene. Hence, this will improve the optical and electrical property of the device. Next, I'm going to discuss on electrical characterization part. Figure 2 shows the light current voltage characteristic of VCSEL devices under continuous wave conditions at room temperature. The maximum light output power is 1.1 milliwatt at injection current of 20 milliampere. The slope efficiency of the device is 0.2 watt per ampere at current less than 12 milliampere. The threshold current is around 1.8 milliampere, which corresponds to the threshold current density of only 2.6 kiloampere per centimeter square, which is achieved with offside aperture diameter of 7 micron. This result shows that there is no serious dislocations are introduced into the laser structure through the regrowth process. The light output power of the device can be further increased by optimizing the bright wavelength of bubble DBR or adjusting the strain of the electric layer. Apart from the light current voltage curve of VCSEL that I discussed just now, I also would like to discuss on the subfigure here, these two subfigure. The first subfigure we can see this is the microscope image of graphene VCSEL with dielectric bubble DBR. And the other subfigure at the bottom right corner here show the lasing of VCSEL tested under the probe. The single mode lasing spectrum of the device is at the bias of 20 milliampere. This type of VCSEL give a single mode light output at wavelength around 858.5 nanometer. We can see that a single and high peak in the graph. This confirms the single mode operation, and the side mode suppression ratio is over 20 dB at room temperature. Here I'm going to discuss on the modulation response for this device. Figure 3 shows the small signal modulation response for the graphene VCSEL that is emitting at 858.5 nanometer for different bias current. A 3 dB bandwidth for graphene VCSEL is compared to the normal VCSEL. For information, electrical 3 dB point is referring to the frequency at which the output electrical power is reduced by 3 dB with respect to the input power. So, the 3 dB bandwidth for graphene VCSEL is 5.91 GHz and the normal VCSEL is 3 GHz. The relatively small modulated bandwidth is probably due to the thermal damping effect that is caused by self-heating regime at large bias current. Moreover, the maximum resonance frequency for the graphene VCSEL can be achieved by further shorts the air gap or reduce the oxide aperture size. So we have finished the discussion for the journal 2. Next we proceed to the journal 3. The topic is effect of the gallium phosphide barrier on efficiency enhancement of 860 nanometer vertical cavity surface emitting laser. We begin with the executive summary for this third journal. So for this third journal also discuss about the VCSEL. As we all know, VCSEL developed in a smaller, smarter devices which requires higher output power. So in order to improve the output power, injection current spreading from electrode to active region must be improved. Gallium phosphide barrier was proposed to obtain a higher current spreading effect in VCSEL. In this research, has been reported that the output power from VCSEL increases with the thickness of gallium phosphide barrier, but it eventually will saturating at for a specific thickness value. According to the computed real emission area and optical property, the current spreading impact in the gallium phosphide barrier is limited by the current window. The optimum thickness gallium phosphide barrier is 3 micron. At this 3 micron, it exhibits the highest output power of 26.5 milliwatt, which is 43% higher compared to the output power from the conventional structure. So this result shows that gallium phosphide barrier used as the current spreading layer is essential for improving the output power from VCSEL of 860 nanometer. The optimal thickness of gallium phosphide barrier in the VCSEL strongly depends on the aperture diameter, or which is also known as real emission area, which can be determined from the current window. So this part explained on the research methodology. First, it started with VCSEL fabrications. This is the structure how it looks like. So for the VCSEL is grown by metal organic chemical vapor deposition system. Next is followed by the gallium phosphide barrier depositions, which is over here. There are 3 thickness grown here, which are 1, 3, and 6 micron thickness. And then the wafer was cleaned with acetone and methanol to remove the organic contaminations. Next is followed by the etching. The end substrate, rear side, and the front side was etched using these solutions. The solutions are made up of sulfuric acid, hydrogen peroxide, and deionized water. Next, followed by the photolithography and selective etching. A ring-shaped pad was patterned on the front side using lift-off photolithography and selective etching. Next is the trench etching. Boron trichloride and argon gas was used to produce a 5 micron deep circular trench for isolation for the light-emitting pole. The trench sample was treated with a 2000 SCCM water vapor flow for 4 minutes at 400 degrees Celsius to form the current window. After the trench etching, it was followed by the baking of the trench. The trench was filled with polyimide and baked for 4 hours at 375 degrees Celsius to stabilize the light-emitting pole. The front side of the substrate were deposited with gold, platinum, and titanium using electron beam evaporator, and the rear side was deposited with gold, germanium, nickel, gold using thermal evaporator. Then the VCSEL chips are ready to be assembled on TO18 package to measure the performance. The characterizations performed includes SAM, emission intensity, measurement, IV, and LI characteristic. Next, I'm going to proceed to result and discussion for journal number 3. The upper part for figure 1 is the SAM images, the cross-sectional images of the structure, and the lower part is just illustrations on the impact of the emission area produced by the current injected from top electrode on the light efficiency of the VCSEL. Okay, next, SAM cross-sectional images shows that, so this one is without any gallium phosphide layer, and these 3 is of different thickness of gallium phosphide layer. A relatively low light efficiency was expected due to small emission area, which can be attributed to the narrow current flow injected from the electrode into the active region. Emission could be remarkably improved by using the gallium phosphide grown on the top dBr of the VCSEL. Based on the emission intensity, which I'm going to show later, the emission area in the active region increases with the gallium phosphide thickness were saturated at the specific thickness corresponding to the thickness of the gallium phosphide barrier. Figure 2 shows the emission intensity from different device configurations. So the black color one is the conventional one. The red is the 1 micron thickness gallium phosphide, and green is 3, blue is 6 micron thickness. So the emission intensity for all these samples are measured at 20 milliampere. And then the sample shows sharp peak at around this 860 nanometer with full width at half maximum of 4 to 5 nanometer. And then next, the peak intensity of this sample shows that the VCSEL chip with this gallium phosphide barrier has significantly higher emission compared to the conventional VCSEL. As you can see, these three red, blue, and green has higher intensity compared to this black color. Black color is the conventional one. And the peak intensity of the VCSEL with gallium phosphide barrier increases with the thickness of the gallium phosphide from 1 micron to 3 micron, but remaining the same at 6 micron. So you can see that the blue and the green one, which is the 3 and 6, is higher compared to the red color line. And the blue and green is almost the same. Next, I'm going to discuss on the electrical characterizations for this VCSEL. We can see from figure 3A is the IV curve, figure 3B is the IL curve. Based on the figure 3A, we can see almost all the samples have the similar IV curve. As for the figure 3B, the output power of VCSEL with gallium phosphide barrier, which is the red and the blue one, is higher compared to the black color line here. Black color is the conventional VCSEL. The VCSEL device with 3 micron gallium phosphide barrier had the greatest output of 26.5 milliwatt among the VCSEL chips with the gallium phosphide barrier. It is 43% higher compared to the conventional VCSEL chips. I would like to continue on the discussions of the IL curve. So if you can see carefully from this figure 3B, the green color and the blue color curve actually is overlapping. This means that the structure of 6 micron gallium phosphide barrier have the same output power as 3 micron gallium phosphide barrier. This could be attributed to the limitation of the real emission region. The optimal thickness of gallium phosphide barrier depends on the real emission area, but its performance could be limited by the current window. So overall, this is to highlight the result shows that the use of gallium phosphide barrier is effective for improving the output power from the VCSEL. This slide shows the overall comparison for these three journals. The three journals are compared in terms of novelty, method of epitaxial fabrications, method of special structure fabrication, lasing wavelength, threshold current, output power, slope efficiency, and side mode suppression ratio. So for the first aspect, novelty. First journal shows the novelty of having this second order grating in the structure. And the second journal shows that a layer of graphene and a low cost dielectric bubble DVR. This is the novelty for the second journal. And the third journal, the novelty part is the additional current spreading layer gallium phosphide in the structure. Next, in terms of epitaxial fabrications, these three journals use the same method, which is MOCVD. As for the method for the special structure fabrication, for the first journal, grating fabrications. The method that they use is electron beam lithography and inductively coupled plasma etching technique. Second journal, the graphene fabrications, the method that they use is copper for losing chemical vapor depositions, and the DVR fabrications, the method that they use is plasma enhanced chemical vapor depositions, PECVD. As for the gallium phosphide fabrications, MOCVD method is used. In terms of lasing wavelength, first journal, the wavelength is 980.1 nanometer. Second and third, almost similar, 858.5 and 860 respectively. As for the threshold current, the first journal shows 300 milliampere, second journal shows 1.8 milliampere, third 10 milliampere. Output power 1.22 watt, 1.1 milliwatt, 26.5 milliwatt. As for the slope efficiency for the first journal is 0.4 watt per ampere, second journal 0.2 watt per ampere, third journal never report this value, this slope efficiency. Side mode suppression ratio for the first journal is 29 dB, and for the second journal is more than 20 dB. The third journal also never report this side mode suppression ratio. Here is the overall conclusion for these three journals. First journal, the conclusion is surface emitting distributed feedback laser SEDFB laser is fabricated with second order grating accompanied with asymmetric waveguide. This SEDFB laser with lasing wavelength of 980.1 nanometer, output power of 1.22 watt, slope efficiency of 0.45 watt per ampere. The threshold current is as low as 300 milliampere. Line width, side mode suppression ratios are 0.84 nanometer and 29 dB respectively. The experimental output power, slope efficiency, and side mode suppression ratio is lower compared to the simulation result. SEDFB laser output properties are the area of improvement focused in the future. As for the second journal, here is the conclusion. BCSEL with top curve, silicon nitride, silicon dioxide dielectric DBR top graphene-based electrode are fabricated. The technique is described for directly grown dielectric bubble DBR structures on graphene half BCSEL via van der Waals force. This primarily based on the graphene function not only as the charge transport channel but also the buffer layer. These BCSELs produce single mode lasers of 858.5 nanometer wavelength, also provide the output power of 1.2 milliwatt, threshold current of 1.8 milliampere are achieved for this device with the 7 micron offset apertures. This prelim result shows the graphene BCSEL structure has the potential for high-speed operation. As for the third journal, the conclusion is BCSEL integrated with different thickness of gallium phosphide layer are fabricated. The lasing wavelength is 860 nanometer. Among all the thickness of the gallium phosphide layer, 3 micron thickness show the highest output of 26.5 milliwatts, which is 43% higher compared to the conventional structure of 18.6 milliwatt. The output powers from the structures with 3 and 6 micron gallium phosphide barrier were nearly equal. These findings suggest that the use of gallium phosphide barrier able to improve the light efficiencies as gallium phosphide layer enhance the current spreading. Furthermore, current spreading also greatly influenced by the aperture diameter, which is defined by the current window in the BCSEL. Lastly, I would like to end this project and presentation with this summary. The three journals selected demonstrated different epitaxial design of surface emitting laser structure. Among these three types of surface emitting laser structures, the most interesting structure I found is that from third journal, the effect of gallium phosphide barrier on efficiency enhancement of 860 nanometer vertical cavity surface emitting laser. The employment of gallium phosphide can be done in other laser structure as well because of its interesting current spreading improvement property. Furthermore, the cuboidal shape of this VCSEL is relatively easier for packaging compared to the SEDVR laser with protruded second order grating, which is from the first journal, or the graphene VCSEL second journal, the structure from second journal with curvature in design. The deposition method of this gallium phosphide layer is through emulsivity, which is the same as the epitaxial structure fabrication. This means that less complexity of fabrication methods compared to other structure. Also, it produced the second high output power among all three surface emitting laser. However, it can be further improved by optimizing the aperture diameter, which is defined by the current window. This journal has clearly shown that the addition of gallium phosphide has the higher emission intensity compared to the conventional VCSEL. Also, this paper reported that 3 micron thickness of gallium phosphide are able to enhance current spreading and thus enhance the output power. Other characteristics such as slope, efficiency, side mode suppression ratio have not been investigated yet. Further confirmation on these two characteristics is needed for future development. That's all from me. Thank you. Thank you again for your attention. That's the end of my presentation.